So this is a video on transformations of parent functions. Before watching this video, check out the previous video on the Desmos, transforming functions in Desmos. It'll give you a little bit more of an intuition before coming to this video. So we have four things that can transform a parent function: a, k, d, and c. And very quickly, a is the thing that vertically stretches or compresses our function. Also can reflect the function in the x-axis if it's negative. K is the thing that horizontally compresses or stretches our function. And if k is negative, it reflects in the y-axis. D moves the graph left or right, and C moves it up or down. The thing that's important about this pattern here, and this pattern is the important pattern to remember about basically how our functions are transformed. Applying this to any function gives you the transformed functions. So the thing to keep in mind here, the thing that's important, is that we have our A and our C values out here. And see how those are outside of this function f? So we have this f here and we have this function here. Everything outside of that is going to be directly transforming our y value, right? So these things here, that's transforming our y values. So I know Miss Andrighetti likes to call this y-land. And inside our function, we have our k and our d values. And those are the things that are responsible for transforming our x coordinates. Those are the things that are inside the function. And we'll call those things, you can probably guess, x-land. We'll see more about how these work in the next page, but let's start off below by listing the transformations with example 1. So, first of all here, this function here, y is equal to negative 2f of 4x. So we actually don't know what f of x is in this case. It could be a quadratic, could be a square root function, could be anything. It doesn't really matter. We're just asked to list the transformations. So what transformations do we have here? We know we have this value here, which is negative 2, right? So this is the a value, right? Because it's out in front. And what other value do we have? We have this 4, right? And that's inside the brackets, inside our f, our function, right? So that is going to be our k value. Now, what are the actual transformations that happen here? First of all, I'm going to start off with a. So what is a going to do to our function? It's a number that's larger than 1, right? Let's forget about the negative for a second. It's a number that's larger than 1. What's that going to do to our function? Well, we know it's going to vertically stretch the function by a factor of 2. Right? So what's next? Let's take care of that negative in front of that a now. What's the negative in front of the 2 going to do? Well, remember this is applied to our a value, and a negative sign just is going to mean that it's going to reflect it in the x-axis, or in the y direction, right, which is the x-axis. So reflection in the y-axis. Sorry, no, in the x-axis, right? It's going to flip that thing below the x-axis, or if it's already below, it's going to flip it above the x-axis. Next, we have our k value. K is 4. This is the tricky one. Remember, is a k value 4 going to compress or stretch that function? We know it's going to be in the x direction, right? That's what k does. Stretches or compresses in the x direction. But what does it do? And when the answer is, if you look above at that table, it tells you that when k is large, bigger than 1, it's going to compress the x values. So it's going to be a horizontal compression by a factor of what? Well, the factor it's compressed by is actually 1 over k, right? So if you remember that. So in this case, it's going to be 1 over 4. So it's going to basically take all the x values and it's going to divide them by 4. And that makes sense. It's going to bring everything closer to that y-axis, right? So if k was like 8, for example, it's going to divide it by 4, and you're going to end up with an x value of 2. Right, in that case. So there we go. Those are the only transformations that are applied to the function in this case. Let's go on to the next one. So this one's interesting. Looks like a normal transformation, but there's one little thing we have to be careful of, and that's to check whether it follows this pattern here at the top of the page. What's different about the pattern we see down here and the pattern we see up here? The answer is the k value. The k value needs to be factored out of everything that's in the bracket. See how there's k and then brackets x minus d? So we basically have to factor that k value out of everything that's inside the brackets, inside this f in x land, right? So let's do that now before we do anything else with this function. So this is going to become y equals negative f, negative 0.5, but what do we get when we factor it out? So when we factor out negative 0.5 from x, it's just going to be x, right? We're just going to divide that by that. And then think about it this way. What are we going to get if we divided that 1 by negative 0.5? That's like multiplying by 2, right? Dividing by 0.5 is equivalent to multiplying by 2. So we're going to end up with negative 2. If that confuses you, just try it. Take the 1 and divide by negative 0.5. That's really what we're doing when we're factoring, right? We're just divide each term by that value that we factored out. And then the 3 doesn't change. The 3 is okay. So now we can find what our values are. What's our a value in this case? Well, there's no number there, so we're just going to assume it's negative 1, right? Don't forget about that negative, though. What's our k value? It's the thing we factored out, right? Negative 0.5. What's this next? So that's right here. What's that next value? Oops, we'll do it like that. What's that next value here? I always forget. Is this the c or the d value? I'm going to check. That's the d value. I don't know why d comes before c, but that's okay. D is it 2 or is it negative 2? Remember, our pattern, sorry to keep zooming out like this, but our pattern has a minus sign in between x and d, right? So in this case, in order for this to be x minus 2, that means d would need to be positive 2, right? So d is 2. It's always the opposite sign of the thing that we see there. And then c is going to be negative 3. That one stays the same. So let's list those transformations. Let's see what's happening here. We're going to start with the a and the k, and then we'll get to the translations later, the d and the c. So transformation 1, let's look at that a value. What is that a value of negative 1 going to do? Well, it's just going to reflect. So reflection in which axis? X-axis, right? Because it has to do with the y values. So the y values basically get reflected in that x-axis. 2, let's look at the k value. What is the, let's forget about the negative sign for a second. What's the 0.5 going to do? Well, just like we talked about in the last one, smaller than 1 is actually going to stretch the function. So it's going to be a horizontal stretch by what factor? By a factor of, well, it's always 1 over k, right? And if k is 0.5, it's going to be 1 over 0.5, which ends up giving us 2. So it's basically a horizontal stretch by a factor of 2. All our x values are going to be multiplied by 2. And then that negative sign in front of the k, let's not forget about that. That's going to give it a reflection in the y-axis. And then we have our d value. Our d value, we call moving left and right and up and down. When you're just moving the function around and not stretching or compressing it, we call that a translation, right? So d is responsible for moving it horizontally. So it's going to be a horizontal translation. Translation is a better word than shift. It's a little bit more technical. Horizontal translation, and what direction is it going to go? Well, if d is positive, it's going to go to the right. So it's going to go 2 to the right. I can squeeze it on the page there. I can just move the page. And lastly, c being negative 3, that's going to be a vertical translation. oops, can't spell, hold on, Tion, 3 down, right? There we go. Those are all the transformations that we can get applied to it. The only thing that was missing from this is a vertical stretch or compression, right? But the rest of the transformations were applied here. So here we're going to actually transform some functions using point mapping. So we're going to take points from our parent function and map them onto the points of the transformed function using this pattern here. So we see the point, the x part of the coordinate from a point on the parent function is going to be transformed using this function here. We're going to divide it by k, the k value, and then add d. And then for the y part of the coordinate, we're going to transform it by multiplying by a and then adding c. The cool thing about using this is all you need is a few points on our initial function, and we can use that to basically find what those final points are on the transformed function. So let's see how this works with an example. I know this question asks us to describe the transformations and stuff like that. Really what we want to do is we want to be able to sketch the function in the transformed function, or the parent function in the transformed function, and then state the domain and range. So that's what we're going to be doing here. We're not going to actually do this part where it says describe the order in which you would apply the transformations. So the parent function we have to deal with, as per the question, is y equals root x. So what are the points going to look like on this function? How are we going to generate the points, basically? And we can do that because we know the x coordinates. We can just plug in some x coordinates, and what it's going to, how we're going to generate the y coordinates is just by taking the square root of those x coordinates. So let's start off with some points that are going to be easy to work with this pattern. For example, let's try point 0, and what would the y coordinate be? Well, just the square root of 0 is 0. Another easy one is 1, because the square root of 1 would just be 1 as well. 2 doesn't work so well with the square root. It's 1.41. It's a decimal. So let's just keep with the easy values. The next easy value would be probably 4, right? 4, 2 would be a next point. The next perfect square would be 9. 9 and 3. And let's just get one more point. I don't know if it's going to fit on our graph, but the next perfect square would be 16 and 4. So we can see these would be the points on our parent function. So let's take a second just to graph these on the graph at the right, and you can go ahead and do that yourself. So we can see that's our parent function. We know the parent function of a root function pretty well, we should, and we know that's what it looks like. So I'm just going to label this as our f of x. That's our parent function. What is the domain and range of this function? Well, just looking at it, we'll do this underneath. So this is for f of x. The domain, x is an element of real numbers such that, well, you can see it ends at 0, 0, right? There's nothing to the left of that. So basically, x has got to be greater or equal to 0, right? That makes sense. And then our range, y is an element of real numbers such that y also, if you look at it, it's going to be everything greater than 0 or equal to 0 as well. So that is our domain and range for our f of x. How do we transform this function now? So this right here is what we have to, that's sort of the transformation map that we have to use in order to find our transformed function. So to do that, first a good idea is to have a bit of a closer look here. Let's identify our a, b, or a, k, c, and d values. So this value 2 out in front, we know that's going to be our a value. What's going to be the k value here? If there's nothing in front of the x, we can assume, well, let's make this 2. Let's assume that the k value is just going to be equal to 1, so that doesn't really matter. This 6, what's that going to represent? That is our d value, right? And lastly, we have this 4, that's going to be our, or sorry, negative 4, which is going to be our c value. C equals negative 4. Sorry, I forgot to do d equals 6, right? Or is it negative 6? Remember, we have to flip the sign there, so it is going to be actually negative 6. So we have our values. Now, we can use this point mapping in order to find out what our transformed function is going to be, because our new x value, when we plug in a value of x, it's going to be transformed by this, x over k plus d. So here, what I can write is I can write what that new x value is going to be. So it's going to be x over k, which is just 1, plus d, which is like minus 6, right? And then our y value is just going to be a times y plus c. So 2y minus 4. And there's our point mapping. I'm actually going to simplify this too. We know the x divided by 1. We can just write that. If I just erase, if I'm able to erase that, I'm just going to make that x, right? X divided by 1 is just going to be x, just to make it a little bit easier to work with. So there's the point mapping for our function. And now all we need to do is plug in the x and y coordinates of each of these points in order to find where they get transformed to. So for example, 0, 0. If we plug in x for 0, we're going to get negative 6. Right? And if we plug in y for 0 up here, 2 times 0 minus 4, we're going to get minus 4. Do the same thing with 1, 1. So 1 minus 6 is negative 5. 1 plugged into that one is 2 minus 4, which is negative 2. 4, 2 is going to get transformed to negative 2, and 4 minus 4, which is 0. 9, 3 is going to get transformed to 3, 2. 16, 4 is going to get transformed to 10, and 4 times 8 minus 4 is 4. So there's our transformed function. So that's each one of those points transformed to its new location. Now what we can do is just graph those points, or as many of those points as will fit on our graph. So go for it, pause the video, and unpause when you're done. So there we go. I plotted those points, and then you can connect them with a nice smooth curve. One way to quickly check, just have a quick look. There were no reflections because k and a were both positive. So it makes sense that this is just sort of that original function but moved around without any real reflections or anything like that. So there we go. Pretty easy, right? You don't have to worry about taking into account all the individual transformations. All you have to worry about is plotting a few points and transforming those few points. So let's find the domain and range of this transformed function, right? So this is the domain and range for 2f(x plus 6 minus 4, right? So what's the domain of this function? We know x is going to be an element of real numbers such that x has to be greater or equal to, that point in there is negative 6, right? And then the range is going to be y is an element of real numbers such that y, again down here we have this point at negative 4. Everything above negative 4 is part of the function, so y is greater than or equal to negative 4. There we go. That's what I wanted from this question. Basically a sketch of the graph of the function, the transform function, and that helps us determine the domain and range of that function. There we go. So let's do a similar thing for this question. Again, I'm not caring so much about the order in which we transform it. I just want to transform this function. The function we're given here is 1 over x, and the transformed function is right here, right? So we want to find the domain and range of those functions. So again, let's start off by saying what our points on our parent function are going to be. They're just going to be x and then 1 over x, right? What do you think are some easy points to plug in here for these? I know what a reciprocal function like this looks like. Some good values might be things like 3, 2, 1, and getting close to that asymptote, maybe something like 0.5 might be handy as well. And then 0, and let's go just to the negative versions of those numbers. Negative 0.5, negative 1, negative 2. That's fine. So between these, we should be able to sort of figure that out. So finding what the y coordinates are for those, 1 over x, if it's 3, is just going to be 1 over 3. I'll leave it as a fraction. It's easy to plot that if it's a fraction. This will be 1 over 2. This will just be 1, right? 1 over 1 is just 1. 1 over 0.5 is going to give us 2. 0 is, well, 1 over 0 is undefined, right? So I'm just going to put UND, standing for undefined, okay? Negative 0.5 is going to give us negative 2 if we divide. This will give us negative 1, and this will give us negative 1/2, right? Had to think about that for a second. Yeah, that's the case. So we should be able to graph that function fairly easily. So go for that now. Try it, and then you can unpause the video. So there's what the function looks like roughly. A little bit hard to draw on an iPad, but that's roughly what it looks like. So now let's do the domain and range for that. So this is for f of x. The domain we know is going to be x is an element of real numbers, such that, are there any restrictions? Well, look at what happens to the x. The x goes across. At 0, it's undefined, and that's actually the same thing that our point said right here. It was undefined at 0. So it's x is an element of real numbers. Everything is okay, but x just cannot equal 0, right? So that is our restriction. And for the range, very similar. Y is an element of real numbers, but we know we have this horizontal asymptote here, so y is basically every value except for 0, right? So such that y cannot equal 0. Okay, so that's our domain for our parent function. Now, the transformed function. So in order to do the transformed function, we have to apply that point mapping again to the points we've already plotted. In order to do that, we need to identify the a, the k, the c, the d value, right? So let's look at this function that we're given here. Negative 2f of 2x plus 8, all minus 1. How do we go about finding those values? Well, first of all, you should notice something about the k value. What's the problem with it? The problem is that it's not factored out. So that's a common mistake. We might think that the d value is 8 or negative 8, but it's not. It's actually something else because we have to factor that out. So easy mistake to make, but try to keep that in mind when you're doing this, not to make that mistake. So I'm just going to rewrite that as y equals negative 2f. Let's factor out that 2. 2x plus 4, right? Double bracket minus 1. So that is our transform function. So just listing off to the side, a is going to equal negative 2, k will equal 2, d, I'm putting the k with the d because those affect the y value, or the x value. D is going to be negative 4, right? It's the opposite of sign of the thing that's in the brackets. And c is going to equal negative 1. So our transformed function, we just have to remember that point mapping once again. And the point mapping for the x was x over k plus d, right? So it's just going to be x over k, which is 2, plus d, in this case is going to be minus 4. So that's our transformation for our x coordinate. And then the y is just going to be, it's just a times y plus c, right? So a is negative 2 times y plus c. In this case, it's going to be minus 1. So there's our transformation. So I want you to pause it here, carry out that transformation for all the points, find what all those points get transformed to, and then plot it and see if you can find your domain and range. So try to do all of that, and when you're ready, unpause it so you can see the answers. So here is the solution to that problem. Transforming the points, you get that red function there. As you can see, the asymptotes of the function have moved. And it's actually easier to plot reciprocal functions like this based on their asymptotes. But for this exercise, we're just doing it based on the points. So you can see the domain and range follow down below. So here's the last question. We have 0.36 on a graph, some transformed graph. We want to find the original point. So basically that 3,6 has been transformed. That is the final location of that point. What was the original point? Luckily, we have a bit of a pattern that can help us here, right? We have a point xy that can be transformed using the relationship x over k plus d for our x part and ay plus c for our y part, right? So all we need to do is identify what those are in our equation. So looking up here, this 2, that's going to be our a value. Our a value is 2, right? What's going to be the d value? Well, it's x plus 1, but remember the pattern is x minus our d value, so that means our d value is negative 1. and our c value is -4. So let's just throw that into our transformation map and see what we can do with that. So x over k is just 1, so it's just going to be x minus 1, right? Our d is -1. And then our y part is just going to be 2y plus c. In this case, c is -4, so it's going to be -4. There we go. So some point xy gets transformed to this, right? We know, though, that these values are also equal to, like this value here is equal to 3, and this value here is equal to 6, right? Because that's given in the question. So essentially, if we know that that's equal to 3, that's equal to 6, we should be able to solve these as equations, right? Just very, very simple equations, right? So essentially what we're saying is that 3 is equal to x minus 1 for that one, and then 6 is equal to 2y minus 4. So we should be able to find our x and our y values from this. So just solving this equation, x is just going to equal 4, right? And y, if we do a little bit of rearrangement here, y should equal, well, we can bring this over, 10 equals 2y. That means y has to equal 5. So our x point is that, our y part of the coordinate is that. So therefore our final point, or our original point I should say, original point is just 4, 5. There we go, and that's the point that got transformed to 3, 6.
Math. Am I right, kids?